I am tracing this wire here. It looks frayed. If that shorts out, we lose ignition to cylinders 3 and 4. The calculations show a high probability of failure within the hour.
January 17th, 1940. Hartford, Connecticut. A bitter winter wind cut across the frozen yards of Pratt and Whitney's sprawling plant. Smoke curled from brick chimneys, mingling with the faint scent of oil and machine grease. Inside, the factory was quiet in pockets. Machines idled, awaiting new orders, while scattered blueprints lay flat on steel tables, ink smudged from hurried hands. Mechanics bent over engine casings, their gloves stained with blackened oil. Sparks flickered from grinding wheels as machinists shaped components that would one day spin high above the Atlantic. Every hammer strike, every measured rotation of a dial, carried weight. The United States had aircraft, but no engines powerful enough for modern combat. In the test hangar, a lone radial engine sat under dim lamps, its cylinders cold, silent. Engineers leaned close, murmuring calculations, tracing wires and fittings with practiced fingers. The stakes were invisible, yet immense. Europe was at war. British and German fighters roared across skies the Americans could only watch from afar. Here, in the hum of a Connecticut plant, the battle for air superiority would begin. Not in the clouds, but in the meticulous turning of metal, in the patience of men determined to build from nothing. The war had not yet knocked at America's door, but the absence of engines made the threat tangible. Time was not a luxury. Every delay carried risk. Every measured success, no matter how small, might decide the future of U.S. air power. From these silent workshops, under the dim glow of tungsten lamps and the persistent chill of winter, the foundations of American aviation were about to be forged from scratch. The question remained, could men and machines rise fast enough to meet a world already at war? By early 1940, Europe was ablaze. Germany had overrun Poland, France teetered under the threat of blitzkrieg, and the skies were dominated by the Luftwaffe. Britain struggled to keep its airspace intact. Radar was still in its infancy, and the Royal Air Force was stretched thin. Across the Atlantic, the United States watched cautiously. The Neutrality Acts constrained direct intervention, yet the nation understood that war in Europe and Asia was not a distant storm. It was a warning. American industry was a marvel of peacetime efficiency. Steel mills, aluminum plants, and machine shops churned out consumer goods, automobiles, and infrastructure. Yet when it came to aviation engines, the picture was starkly different. U.S. aircraft designs existed in quantity, but the engines powering them were largely obsolete. Piston engines lacked the horsepower to lift fully loaded bombers or sustain high-altitude fighters for long missions. Radial engines, reliable and robust, were available in limited numbers, but American designs lagged behind European innovations. British Rolls-Royce Merlin engines and German Daimler-Benz power plants pushed aircraft to heights, speeds, and endurance that U.S. aviation could only aspire to replicate. Pratt Whitney, headquartered in Hartford, Connecticut, had earned a reputation for durable radial engines during the interwar years. The Wasp and Hornet series powered both military trainers and commercial aircraft. Yet in 1940, even their most advanced engines were inadequate for the looming conflict. The challenge was not merely mechanical, it was industrial. The U.S. lacked the specialized tooling, assembly lines, and mass production protocols to create high-output engines at the scale Europe demanded. Every component, from the forged crankshaft to the finely machined cylinder head, required exact tolerances, and existing facilities were designed for small orders rather than wartime output. The government's role in aviation had been limited but growing. The Army Air Corps, under Major General Henry H. Arnold, had begun emphasizing modernization, but budget constraints and inter-service debates slowed procurement. Congressional hearings in 1939 and early 1940 revealed a sobering reality. The United States could neither produce the aircraft nor the engines required to match Axis capabilities in sustained air campaigns. Forecasts suggested that without immediate industrial action, American forces would face a severe disadvantage if war spread to the Western Hemisphere. Pratt and Whitney engineers understood the implications. Every failure in design, every delay in testing, would ripple far beyond the factory floor. In one workshop, machinists assembled crankcases while engineers reviewed performance charts, comparing projected horsepower against structural stress limits. They pored over sketches of cylinder arrangements, valve timings, and ignition systems, knowing that a single miscalculation could compromise both reliability and efficiency. Across the plant, test stands sat idle, awaiting engines that did not yet exist in fully functional form. Compounding the challenge was material scarcity. Aluminum, critical for lightweight engine components, was in high demand for civilian aircraft and automobiles. Steel production prioritized infrastructure and armaments. Copper, magnesium, and nickel, all essential for engine construction, were tightly rationed. Pratt and Whitney had to design engines that could maximize power while minimizing reliance on strategic metals. Every piston, every bearing, every spark plug became a calculated choice between performance and feasibility. The urgency intensified as Britain began requesting Lend-Lease support. American policymakers realized that if the U.S. was to provide meaningful aid, engines capable of propelling bombers and fighters were non-negotiable. The task was unprecedented. Develop new engines from scratch, ensure reliability under combat conditions, and do so before the war reached America's shores. Every day lost in design or testing increased the technological gap between Allied expectations and American capacity. At the same time, intelligence reports trickled in. German aircraft were advancing rapidly. Messerschmitt Bf 109s and Focke-Wulf FW 190s demonstrated superior climb rates and high-altitude performance. British Spitfires and Hurricanes, though effective, relied on Merlin engines pushed to the edge of their limits. U.S. aircraft, in contrast, could barely maintain pace in simulated performance tests. In Hartford, engineers and managers faced a stark truth. The nation's industrial might was unmatched in peacetime, but in aerial warfare, it was still an apprentice. The decision was clear. Pratt and Whitney had to build engines from scratch, not mere upgrades. They had to engineer radials that could endure long missions, high altitudes, and sustained stress, all while being produced in volumes previously unimaginable. Testing rigs were expanded. Material suppliers were consulted directly to secure metals in exacting specifications. The factory floor became a laboratory, a proving ground, and a quiet battlefield of its own. Even outside the plant, the stakes were visible. Aircraft designers sketched fuselages capable of supporting heavier power plants. Pilots evaluated mock-ups for weight distribution and center of gravity. The Army Air Corps, while cautious, began simulating deployment scenarios, calculating fuel consumption, range, and payloads against engines still in development. Every calculation underscored the urgency. Failure was not theoretical. It was existential. By mid-1940, Hartford's workshops were humming, a mixture of anticipation and anxiety vibrating through every bolt and piston. From the cold concrete floors to the high ceilings streaked with winter sunlight, the task was clear: build radials capable of transforming U.S. aviation from outdated trainers to engines of modern air power. The world's conflict waited for no one, and neither would history forgive hesitation. The success or failure of this effort would determine more than machines. It would determine America's readiness to project power across oceans. And every late night, every clanging of metal against metal, brought the engineers closer to bridging the gap between potential and performance. By the late summer of 1940, the war in Europe had hardened into a grim reality. France had fallen. Britain stood alone, battered yet defiant, and the Luftwaffe's dominance over continental airspace was undisputed. Across the Atlantic, U.S. military planners realized that their window for preparation was narrowing. The need for modern, reliable aircraft engines had shifted from academic concern to strategic imperative. Pratt Whitney's task had grown more urgent. It was no longer about keeping pace. It was about leapfrogging. Design teams converged in Hartford's main engineering halls, their desks covered with blueprints, charts, and hand-drawn schematics. Each radial engine proposal went through meticulous scrutiny. Cylinder bore sizes, compression ratios, and valve timing sequences were analyzed repeatedly. Every material specification was weighed against supply constraints. Magnesium could save weight, but burned if mishandled. Aluminum could reduce mass, but softened under heat. Steel was durable, but heavy. The challenge was to create a combination that offered maximum performance without overtaxing American industry. Prototype construction began in small batches. Each crankshaft was hand-fitted, every bearing checked and double-checked. Test stands, long rows of heavy steel and timber, echoed with the rhythmic clank of turning engines. Observers recorded torque, revolutions per minute, and thermal stress. Failures were frequent. Pistons cracked, bearings seized, valves warped. Yet with every setback, engineers refined tolerances, adjusted materials, and modified cooling systems. The failures, though frustrating, were instructive. They revealed weaknesses that could be corrected before full-scale production. Concurrently, the government provided cautious support. The Army Air Corps allocated funds for high-output radial engines, prioritizing the most promising prototypes. Material allocation improved, though it remained insufficient for rapid mass production. Civilian demand still competed for aluminum and steel, and rationing regulations limited flexibility. Yet Washington recognized the stakes. Modern engines meant longer-range bombers, faster fighters, and a credible air deterrent. Pratt & Whitney was not building machines. They were building the backbone of American aerial defense. Testing was relentless. Prototype engines underwent continuous operation for days at a time, simulating missions at varying altitudes. Cooling fins were adjusted to dissipate heat efficiently. Ignition systems tweaked for reliability, and lubricants tested under extreme conditions. Every malfunction triggered a rigorous postmortem. Engineers dissected components, measured metal expansion, and refined machining techniques. The process blurred the line between research and manufacturing. The factory itself became a laboratory, every assembly line a controlled experiment. Beyond mechanics, human endurance was tested. Engineers, machinists, and technicians worked long hours in dimly lit shops, the air filled with fumes of lubricants, solvents, and heated metals. Wartime urgency imposed psychological pressure. Mistakes were costly, not just in lost time, but in delayed readiness for an uncertain war. Many staff slept in small cots along the walls, their notebooks open beside them, recording late-night calculations. Fatigue and focus intertwined. Precision demanded alert minds, yet the workload often pushed them past exhaustion. The first successful WASP radial prototypes demonstrated the potential. Output power increased significantly, cylinders cooled efficiently, and engines survived extended test runs without catastrophic failure. These successes were measured, quiet, but undeniable. Military liaisons noted the improvements and began coordinating with aircraft designers. Engine dimensions, weight, and output were integrated into bomber and fighter designs. This collaboration laid the foundation for a production pipeline that would later support tens of thousands of aircraft across multiple theaters. Meanwhile, intelligence reports highlighted the accelerating pace of German and British engine development. The Bf 109's Daimler-Benz DB601 engine and the Spitfire's Merlin outperformed many American Radials in speed and altitude. The comparison underscored the urgency. Pratt Whitney could not merely match European designs. They had to exceed them. Each enhancement in compression ratio, cooling efficiency, or weight reduction represented not just engineering skill, but strategic advantage. By late 1940, Hartford's factories had achieved a quiet transformation. Prototype designs had stabilized, production procedures were formalized, and the first small runs of high-output radials were ready for Army evaluation. The engines themselves were proof that American industry could innovate under pressure, translating theoretical designs into functional, reliable machines. The groundwork for mass production was laid, even if the scale had yet to reach wartime volumes. These efforts had implications far beyond the workshop. They signaled the beginning of America's ability to sustain large-scale air operations, support allied nations, and eventually project power across oceans. Every crankshaft, piston, and cylinder produced in Hartford contributed to a broader strategy that U.S. industry could transform potential into capability before the nation was forced into total war. The stage was now set for the next phase, scaling these engines for mass production, integrating them into new aircraft designs, and ensuring that the United States could meet the coming conflict with both quantity and quality. The leap from prototype to battlefield readiness would define the nation's early wartime aviation posture, and the engineers who labored in Hartford would become unsung architects of air power. The story of Pratt and Whitney's Radial engines in 1940 could be examined through multiple lenses, each revealing a different dimension of the effort and its consequences. The first is the human angle. Hartford's factories were filled with engineers, machinists, and draftsmen who had been trained in peacetime routines, yet now faced a war-driven tempo that allowed no margin for error. Each man and woman worked under dim tungsten lights, surrounded by the constant hiss of compressed air, the smell of lubricants, and the heat of running engines. Fatigue etched lines into faces that were already streaked with grease and soot. Yet determination persisted. Small victories, a cylinder that held pressure, a crankshaft that rotated smoothly, were celebrated quietly. There were no parades, no medals, only the steady accumulation of knowledge and skill. In those workshops, human endurance became as critical a component of engine reliability as the metals themselves. The technological angle highlights the engineering breakthroughs that made radial engines feasible under wartime constraints. Radials had existed for decades, but the demands of modern combat required unprecedented power-to-weight ratios, thermal stability, and reliability. Engineers experimented with new alloys and heat-treating methods, balancing aluminum and steel to withstand high compression while minimizing weight. Cooling fins were refined to optimize airflow across cylinders at varying altitudes. Lubrication systems were redesigned to prevent oil starvation during steep climbs or tight maneuvers. Each innovation was incremental, tested, and refined under strict quality control. Failure was instructive. A cracked cylinder or a warped valve revealed weaknesses that might have been fatal in a dogfight, but in Hartford, they became guides for improvement. From a tactical angle, the significance of the radial engine extended beyond factory walls. Pilots depended on engines that could endure long missions, rapid climbs, and sustained firing from mounted guns without faltering. Engine reliability determined whether a bomber could reach Berlin, whether a fighter could escort convoys across the Atlantic, or or whether a training aircraft could bring a new pilot safely home. Each would have power, an ounce of weight savings translated directly into operational flexibility, range, and survivability. In a conflict where the skies over Europe and the Pacific were contested, the quality of American engines would determine the margin between victory and disaster. The industrial angle reveals the broader context of production. Before the war, the United States had capacity, but not the processes to mass-produce high-performance engines at scale. Factories built for consumer machinery had to be converted, assembly lines reorganized, and skilled labor trained to new tolerances. Every component, from a connecting rod to a precision bearing, had to meet exacting standards. Supply chains were fragile. Aluminum shipments competed with civilian aircraft, steel was rationed, and new materials were scarce. The challenge was not only to design an engine that worked, but to create a production pipeline capable of turning out thousands of them without sacrificing quality. Hartford became a prototype of wartime industrial adaptation, proving that innovation and scale could coexist. A leadership angle emphasizes the coordination between engineers, military liaisons, and corporate executives. Pratt and Whitney management had to balance innovation with deadlines, encouraging experimentation without allowing it to derail broader production goals. Military observers monitored progress, providing technical requirements, testing support, and strategic guidance. Decision-making required both patience and decisiveness. A single misallocation of materials or personnel could delay engine availability for months. Leadership success was measured not in speeches or recognition, but in the quiet delivery of engines that met exacting specifications. The strategic angle situates the engines within a larger scope of national defense. The United States, though still neutral in 1940, recognized the trajectory of global conflict. If Britain fell and the Axis advanced unchecked, American industry would need to project power across oceans. Engines were more than machines. They were enablers of strategy, the mechanical heart of bombers, fighters, and reconnaissance aircraft. Every technical achievement in Hartford had geopolitical consequences, shaping the nation's ability to influence the war before even entering it. Through these angles, human, technological, tactical, industrial, leadership, and strategic, the story of Radial engines emerges as a multidimensional achievement. Each perspective underscores a different facet of the challenge. The fatigue and ingenuity of workers, the subtle art of metallurgy, the direct link between machine performance and combat outcomes, the orchestration of industrial resources, and the alignment of innovation with national defense. Together, they reveal that what was happening in Hartford in 1940 was far more than factory work. It was preparation for a war whose scale and intensity would soon engulf the globe. Continuing from the first section, we can explore additional angles that deepen understanding of the Pratt and Whitney effort in 1940 and early 1941. One critical perspective is moral and ethical responsibility. Engineers and factory managers were aware that the engines they produced would carry men into battle, often over hostile skies. A failed cylinder or miscalculated tolerance could result in a pilot's death hundreds of miles from home. This knowledge instilled a quiet gravity into every task. There were no medals for avoiding errors in a workshop. The reward was simply ensuring that each engine met the uncompromising standards demanded by lives on the line. The moral weight of precision transformed routine production into a solemn duty, a silent pact between engineer and aviator. The logistical angle illustrates the immense complexity of wartime production. Engine manufacturing required coordination across multiple suppliers, each providing specialized materials and components. Aluminum had to arrive from smelters, steel castings from foundries, and rubber seals from chemical plants. Delays or impurities anywhere along this chain could stall entire assembly lines. Transportation networks, railroads, trucks, and ports had to function flawlessly often under the threat of natural or human disruption. In this environment, success depended not only on technical skill, but also on meticulous scheduling, inventory management, and foresight. The logistical dance behind every Pratt Whitney engine was invisible to the pilots who relied on them. It was as crucial as the pistons and cylinders themselves. From an enemy perspective, the significance of these engines becomes clearer. Axis powers were producing high-performance aircraft of their own, pushing the limits of speed, armament, and altitude. The reliability and availability of American radial engines would determine whether U.S. aircraft could compete in sustained air campaigns. If engines failed, American planes could not escort bombers, defend shipping lanes, or contest air superiority over critical theaters. In this sense, the seemingly mundane work in Hartford had direct strategic consequences for the balance of power overseas. The success or failure of these factories would ripple across the skies of Europe and the Pacific, affecting engagements far beyond Connecticut. A scientific and technical research angle emphasizes the leap in engineering knowledge required to build radial engines from scratch. Pratt & Whitney's teams were not merely repeating existing designs. They were pushing materials science, thermodynamics, and mechanical engineering into new territory. Precision machining at tolerances previously reserved for laboratory instruments became standard practice. Lubricants had to endure extreme temperatures without degradation, and new alloys were tested for both durability and manufacturability. Engineers kept meticulous notes on each experiment, feeding lessons from failed prototypes directly into the next production iteration. The factory itself became a living laboratory, blending theoretical research with practical application under the relentless pressure of looming conflict. The training and workforce development angle also played a critical role. Radial engine production required workers to master intricate skills rapidly. Apprentices and machinists were retrained, learning the nuances of tolerances, heat treatment, and assembly protocols in a compressed time frame. Mentorship and hands-on guidance were essential, and experienced engineers frequently oversaw every step of the process. This accelerated education not only enabled immediate production goals, but also built a cadre of skilled labor that would serve the U.S. aerospace industry for decades. The human capital developed during these years became as valuable as the engines themselves, a hidden legacy of wartime urgency. Finally, the economic and industrial policy angle highlights the intersection of government, corporate strategy, and national security. Pratt & Whitney operated under contracts that linked production targets to national defense needs, but the company also had to navigate resource allocation, pricing, and efficiency. The War Department provided oversight, yet expected the company to innovate within constraints, producing engines that were reliable, reproducible, and scalable. Decisions made in boardrooms and offices, often hundreds of miles from the factory floor, determined which materials were prioritized, which production lines expanded, and which technological risks could be tolerated. The alignment of private industry and public interest in Hartford exemplified the broader U.S. strategy of leveraging industrial strength as a decisive wartime advantage. Taken together, these angles, moral responsibility, logistics, enemy perspective, scientific innovation, workforce development, and industrial policy, offer a comprehensive view of the radial engine effort. Each dimension underscores the intricate interplay of people, technology, and strategy. The Hartford factories were not isolated sites of manufacture. They were a microcosm of a nation preparing for global conflict, a place where technical mastery and human resilience converged to shape the outcome of the Second World War. January 1941. The Hartford skyline was gray under a winter sky, smoke curling from factory chimneys into the icy air. Inside Pratt & Whitney's main assembly hall, the rhythm of hammers, presses, and grinding wheels was relentless. Hundreds of workers moved with quiet intensity, eyes fixed on engine blocks, pistons, and crankshafts. Each radial engine on the line represented not just metal and machinery, but the lives of pilots who had yet to take to the skies. On the floor, machinists measure tolerances with micrometers, fingers numb from cold despite the heat of the furnaces. A single misalignment, a cylinder slightly off, a bolt torque miscalculated, could translate into engine failure thousands of miles away, over hostile territory at 20,000 feet. The stakes were immediate. The United States did not yet have a large operational air force. Existing planes required engines that could endure the stresses of combat, long missions, and extreme temperatures. The margin for error was vanishingly small. Across the hall, engineers huddled over blueprints, revising specifications for the latest batch of our 1830 radials. They had been testing a new alloy for cylinder heads, designed to resist overheating during sustained climbs. Earlier prototypes had failed, metal warped under stress, and lubricants broke down in ways the engineers had not anticipated. Each failure had been logged meticulously, analyzed, and integrated into the next design. Now, they were pushing the machines beyond anything America had built before. The hum of the test stands underscored the tension. Each engine run a live experiment with consequences far beyond the laboratory. Meanwhile, in a nearby office, management and government liaisons coordinated production quotas, material shipments, and labor schedules. Aluminum from Pittsburgh, steel from Bethlehem, rubber from Akron. Every resource had to arrive on time. Delays could ripple through the entire production chain, slowing the delivery of engines critical to training pilots and equipping aircraft. The War Department monitored every output report, cross-checking performance, reliability, and delivery against projected needs. Failure was not an option. Improvisation was tolerated only when it led to a measurable improvement. January 17th, 1941, marked a crucial test. Pratt Whitney scheduled the first full-scale run of the new R 1830 series engine designed for extended combat performance. On the test stand, engineers adjusted valves, monitored fuel flow, and checked ignition timing. Outside, the New England winter wind rattled the windows, but inside, the room was tense with heat, sound, and anticipation. Every measurement, every spark, every tremor of the crankshaft mattered. Technicians leaned in, watching gauges that flickered under fluorescent lights. The engine roared to life, a mechanical heartbeat echoing through the hall. For minutes, the engine ran flawlessly. Cylinders held against the heat, oil pressure remained steady, vibration stayed within tolerances. A collective breath seemed to be released, yet the celebration was muted. Engineers knew that this success, while vital, was only the first step. Engines had to be produced repeatedly, in dozens, then hundreds without variation. Every unit destined for training bases, overseas squadrons, and eventual combat would be scrutinized with the same exacting standards. At the same time, intelligence from Europe underscored the urgency. The Luftwaffe's newest fighters and bombers were pushing the limits of speed and altitude. British reconnaissance reports indicated that engine failures had grounded some RAF aircraft in North Africa. Each mechanical mishap translated into lost territory, missed missions, and casualties. America's radial engines were now part of a global race. Pratt & Whitney had to ensure that U.S. aircraft would not be at a disadvantage, that American planes could ascend, maneuver, and endure in ways that rival designs could not. Back on the floor, machinists rotated between assembly lines, fitting crankcases, connecting rods, and cylinders with painstaking care. Apprentices observed, learned, and repeated procedures under the guidance of veteran machinists who had spent decades in precision engineering. The hall was a choreography of discipline, a testament to the convergence of skill, coordination, and national urgency. A misstep anywhere could result in hours of rework, wasted materials, or worse, defective engines reaching pilots in training or deployment. By mid-afternoon, The test engines were dismantled, inspected, and reassembled for the next run. Engineers debated minor adjustments: timing, fuel ratios, cooling systems. Each discussion measured against historical data, metallurgy research, and projected operational conditions. Across Hartford, other workshops mirrored this intensity. Gear cutting, piston fitting, and crankshaft balancing happened simultaneously, each operation feeding into the next. The factories were a networked organism, alive with the pulse of industry mobilized for survival. Even as success mounted, there was no certainty. Every breakthrough demanded repetition. Every lesson learned required dissemination across dozens of workstations and hundreds of personnel. The engines were not merely machines. They were a promise. A promise that the United States could transform from a nation unprepared for global air combat into one capable of sustained, large-scale aerial warfare. The line between laboratory success and operational readiness was narrow, and Pratt and Whitney stood at the edge, balancing innovation with discipline under the looming shadow of a world at war. And as the winter dusk fell over Hartford, the mechanical hum gave way to quiet reflection. Outside, the city was cold and gray. Inside, a nation's future in the air was being forged in metal, sweat, and precision. The engines on the test stands had passed their first crucial hurdle, but the real challenge, replicating this success across hundreds of units under the relentless pressure of impending conflict, was just beginning. Spring 1941. Pratt & Whitney's production halls had grown louder, larger, more structured. Lines of radial engines moved like clockwork across the floor. Workers, now practiced in the rhythm of high-pressure production, had developed an almost military precision. Each engine was measured, adjusted, and tested in exacting sequence. The hum of machinery punctuated by the occasional clank of metal or hiss of steam. By now, the stakes had multiplied. The United States remained officially neutral, yet intelligence reports painted a world already consumed by conflict. The RAF struggled to replace lost aircraft. The Luftwaffe pushed bombers across Europe, and Japanese expansion in the Pacific threatened supply lines critical to Allied survival. The pressure on Pratt & Whitney was no longer just industrial. It was geopolitical. American engineers were tasked with preparing the nation for a war that had not yet fully reached its shores. Each engine had to meet specifications that mirrored combat conditions the United States had yet to face firsthand. In one corner of the hall, a group of metallurgists examined cylinder heads under bright tungsten lights. They adjusted cooling fins, tested alloy mixtures, and tracked thermal expansion. Anomalies were logged immediately. Nothing was left to chance. Failures at this stage could be catastrophic later. One miscast cylinder might ripple through dozens of engines, undermining the reliability of aircraft that would eventually fly over hostile skies. These men and women understood that meticulous work on the factory floor could save lives thousands of miles away. Meanwhile, supervisors coordinated material flow with military liaisons. Aluminum, steel, and magnesium shipments had to arrive on strict schedules. Delays in procurement threatened not only production quotas, but the credibility of the United States' emerging air power. Engineers mapped each component, anticipating shortages and recalibrating workflows to maintain output. The balance between innovation and efficiency was delicate. Every adjustment demanded foresight. Engines had to be stronger, lighter, and more heat-resistant than any previous American design. April 1941 brought a decisive test. Pratt & Whitney scheduled a mass run of our 1830 engines, now optimized with improved cylinder heads, reinforced crankshafts, and new lubrication systems. Test stands filled with humming engines, vibrating in unison. Engineers monitored gauges, checked oil pressures, and recorded temperatures with precision instruments calibrated to fractions of a degree. A single gauge fluctuation could mean redesign, delay, or failure. Outside, the world's skies roiled with conflict. Reconnaissance planes over Europe reported losses, engines catching fire mid-flight, aircraft grounded by mechanical failures. America's lack of operational experience in these conditions magnified the importance of flawless production. The Radial engines rolling off Hartford floors were intended to close that gap. They were America's promise to pilots who had not yet flown, to squadrons not yet formed, and to a nation preparing for the inevitability of war. On the floor, machinists rotated through specialized stations, crankshaft balancing, connecting rod installation, cylinder head assembly. Apprentices and veterans worked side by side, teaching, learning, repeating procedures to minimize human error. Each engine that passed inspection represented not just mechanical success, but the cumulative knowledge of years of engineering and the immediate application of wartime urgency. The factory was no longer a place of isolated research. It was a living organism, every part dependent on the precision and expertise of the whole. By mid-afternoon, the results of the mass run were analyzed. Engines that had been meticulously tested now faced simulated combat conditions, high RPM, extended duration, sudden thermal spikes. Observers recorded every vibration, every temperature fluctuation, every sign of material fatigue. The data confirmed what engineers had hoped. The R-1830 Radials could operate reliably under stress approaching that of combat missions. The engines had transformed from experimental prototypes into production-ready machines capable of sustaining America's future air operations. Even as the factory buzzed with cautious relief, the true scale of the challenge loomed. Replication across hundreds of units, under accelerated wartime timelines, would test logistics, supply chains, and human endurance. Yet the groundwork was laid, design flaws corrected, material limits understood, processes standardized. The United States now possessed an industrial mechanism that could convert raw resources into reliable aircraft engines, a capability absent barely a year earlier. By the end of April, Pratt Whitney had completed the first full production batch. Engines were crated, shipped, and prepared for deployment to training bases and overseas missions. Government inspectors documented each step, noting performance metrics, repeatability, and reliability. The War Department, cautious yet optimistic, recognized that the nation was no longer entirely unprepared in the air. The mechanical heartbeat of the United States' future aerial power now had a body, radial engines capable of carrying pilots into combat with confidence. Winter had given way to spring, and the factory floors, once chaotic with experimentation, now hummed with disciplined efficiency. The turning point was clear. What had begun as a desperate scramble to build engines from scratch had evolved into a robust industrial solution. Pratt & Whitney had not merely created machines. They had engineered America's entry into sustained, modern aerial warfare. The nation's industrial capacity had caught up with its strategic necessity. As crates of engines left Hartford for military installations, the gravity of the moment settled over the engineers and machinists. Every turn of the crankshaft, every meticulously fitted cylinder, had bridged the gap between potential and preparedness. The United States had moved from a nation watching war unfold abroad to a nation capable of producing the engines that would carry it decisively into global conflict. With production stabilized and the first operational engines distributed, the focus shifted to the next challenge, scaling output to meet the rapidly expanding needs of an air force about to engage the world's most advanced aircraft. The victories on the factory floor were only the beginning, the war in T. By late 1941, the first American-built radial engines had reached operational units. Training squadrons across the continental United States received R-1830 engines mounted in BT-13s, P-30SXS, and early B-17 bombers. Mechanics inspected, greased, and calibrated every moving part, aware that the slightest defect could compromise flight safety. The hum of ground tests filled airfields at dawn, fog curling over tarmac, pilots leaning over cowlings, their breath visible in the chill morning air. For many, it was the first time an engine they could trust replaced uncertainty with reliability. Across the Atlantic, reports of British and German air operations underscored the stakes. The Luftwaffe's twin-engine fighters, like the Messerschmitt Bf-110, had already demonstrated the devastating consequences of superior engine performance. American planners understood that quantity alone would not suffice. Quality and consistency were essential. Each R 1830 rolling off the Pratt and Whitney line represented a direct response to a world in which mechanical failure meant death and defeat. The first combat deployments of American aircraft powered by these engines were limited but telling. Observers noted that maintenance cycles were shorter than expected, and the engines withstood repeated high-altitude operations. In training exercises simulating long-range bombing runs, Radials performed without overheating or catastrophic failure, a dramatic improvement over earlier designs. These successes, though quiet, began shifting the perception of American air power from theoretical potential to tangible capability. Pratt and Whitney's industrial achievement also influenced strategic decisions in Washington. The War Department, previously cautious in allocating resources to engine production, now increased orders, investing in new tooling, assembly lines, and training programs for machinists and engineers. This decision marked a turning point. The United States was no longer improvising. It was intentionally building the backbone of a future Air Force. Each additional engine meant more bombers could be deployed overseas, more fighter squadrons could be trained, and more pilots could fly with confidence. On the factory floors, lessons from early experiments were codified. Quality control teams meticulously documented tolerances, failure rates, and material properties. Engineers refined cooling fins, improved carburetor designs, and standardized assembly procedures. Apprentices learned not only technical skills, but the importance of precision under pressure, an ethos that would carry into wartime production at massive scale. Every R 1830 was now a product of disciplined methodology rather than isolated innovation. The impact extended beyond the immediate military sphere. Aircraft manufacturers, previously constrained by engine availability, could plan new models with higher performance thresholds. The Boeing B-17, Douglas C-47, and later the P-47 Thunderbolt all benefited indirectly from the Radial engine program. Engineers could design airframes with confidence that the power plants would meet operational demands. American aviation, once a patchwork of experimental designs, now had a dependable foundation on which to expand. Internationally, Axis observers noted America's industrial progress, though they did not yet fully grasp its scope. Germany's intelligence reports mentioned the expansion of U.S. engine factories, and Japan monitored production in Hartford and Connecticut, recognizing that reliable engines would soon enable American aircraft to match or exceed their own operational ranges. The psychological effect of these developments, while not immediately evident on the battlefield, planted seeds of concern among enemy planners. Even in peacetime terms, the program represented a major technological leap. American metallurgy had been pushed to new limits. Tooling and machining practices had been refined under extreme schedules, and large-scale coordination between private industry and government agencies had been proven. The Radial engine program became a template for other wartime production efforts. Propellers, landing gear, fuselage assemblies, and eventually naval engines followed the same logic of rapid industrial adaptation under pressure. As 1942 began, the United States had achieved more than just functional engines. It had established a repeatable, scalable process for producing high-performance radial engines capable of supporting sustained aerial campaigns. The foundation was in place. From Hartford to airfields overseas, American aircraft were now powered by engines that could endure the extremes of combat, giving pilots a reliability they had previously lacked. This quiet victory in engineering and industrial coordination set the stage for the full mobilization of U.S. airpower after Pearl Harbor. The engines had proven themselves, but the war was far from over. The challenges of mass deployment, integration into new airframes, and expansion to support global operations were only beginning. By spring 1942, the scale of American engine production had begun to shift the balance of possibility. Factories in Hartford, Connecticut, and surrounding towns hummed with activity, machine tools churning, and components moving along conveyor lines in a coordinated dance of industrial efficiency. Every crankshaft, piston, and cylinder bore the mark of meticulous measurement. Every engine leaving the plant represented not just mechanical function, but the cumulative knowledge of months of experimentation, testing, and refinement. Mechanics on the front lines quickly appreciated the difference. In North Africa, pilots of early B-17 deployments noted that their engines maintained power over long desert crossings where heat and sand had previously been catastrophic. In the Aleutians, crews flying against relentless weather discovered that the Radials, though heavy, delivered steady performance despite ice, fog, and corrosion. Reliability, once a rare commodity, was now becoming standard. Pratt and Whitney's accomplishment also altered the strategic calculus in Washington. Military planners could now schedule training and deployment with unprecedented confidence. Aircraft production goals could be ambitious rather than cautious. The knowledge that engines could endure repeated operational stress meant bomber wings could be built larger, fighter squadrons could extend patrols farther, and the U.S. Army Air Forces could plan offensive operations across multiple theaters simultaneously. The impact of engine reliability reverberated across every level of strategy. Behind the scenes, the lessons of 1940 to 1941 continued to influence industrial policy. Material science, previously an academic concern, became a cornerstone of wartime planning. Metallurgical engineers collaborated with designers to anticipate failures before they occurred, and chemical processes for steel and aluminum refinement were scaled to keep pace with the demand for durable, heat-resistant engine components. Production lines became laboratories, and every wartime innovation contributed to a growing institutional memory of technical resilience. Meanwhile, the global context amplified the significance of these achievements. In Europe, the Luftwaffe continued to operate high-performance fighters, but sustained attrition was increasingly favored by Allied numerical superiority. In the Pacific, Japan's long-range aircraft faced logistical limitations. By ensuring that American engines could perform consistently in multiple environments, the U.S. effectively widened its operational reach. Each reliable engine represented not just a machine, but a strategic lever capable of influencing distant battlefields. Industrial coordination between private manufacturers and government agencies also became a model for subsequent programs. Propeller production, avionics, and even naval engines followed a similar pattern of early experimentation, rigorous testing, and systematic scaling. Lessons learned from radial engine production informed the assembly of the P-47 Thunderbolt's massive Pratt and Whitney R-2800 double Wasp engine, which would later dominate both European and Pacific theaters. The success of 1940 to 1942 production planning created a blueprint for integrating complex engineering into mass wartime mobilization. The human element remained critical. Workers, engineers, and supervisors endured long shifts, often under the stress of looming deadlines and the moral weight of war. Mistakes were rare but costly. Every flaw could delay a bomber deployment or compromise a pilot's survival. Yet the teams persisted, motivated less by recognition than by the understanding that their work enabled victory. Across workshops and test facilities, The hum of engines under assembly became a symbol of national resolve, a quiet rhythm that echoed through every bomber hangar and airfield. By mid-1943, the full impact of the engine program was clear. American airpower, previously constrained by unreliable or inconsistent power plants, now had a foundation capable of supporting sustained campaigns across continents. Engine reliability allowed the United States to project power over unprecedented distances, maintain logistical momentum, and coordinate complex operations involving multiple aircraft types. The war's technological trajectory had shifted. The combination of industrial foresight, chemical expertise, and mechanical innovation had created a decisive, if understated, advantage. As the conflict progressed, engines continued to evolve, but the lessons from the initial Radial program remained embedded in every new design. The collaboration between scientists, engineers, and military planners created a model for turning experimental knowledge into operational capability. From the factory floor to the cockpit, the principles of precision, reliability, and incremental improvement became inseparable from U.S. airpower. Ultimately, the aftermath of 1940 to 1942 demonstrated that victory depended as much on preparation, discipline, and innovation as it did on tactics or bravery in battle. By mastering the Radial engine, the United States had not merely produced machines. It had constructed the industrial and technical scaffolding necessary for sustained global operations. That achievement, quietly realized in workshops, test cells, and assembly lines, would reverberate through every aerial campaign that followed. The story of America's Radial engines in 1940 to 1942 is not one of spectacle, medals, or dramatic dogfights. It is a story of preparation, of quiet determination, and of the unseen architects of war who shaped victory long before the first bombs fell. In dimly lit factories and chemical labs, engineers measured tolerances by the thousandth of an inch, tested materials to their breaking points, and recalibrated designs under relentless pressure. Each decision carried weight, not only for the machine, but for the men who would rely on it thousands of miles away. This era of innovation illustrates a profound truth. Modern warfare is as much a contest of knowledge, industry, and foresight as it is of strategy and courage. Aircraft engines, often overlooked in popular histories, became the fulcrum upon which the United States leveraged its industrial power. Without reliable radials, bombers could not reach distant targets. Fighters could not sustain patrols over hostile skies. Every flight powered by a Pratt Whitney engine represented the culmination of months of experimentation, a bridge between theory and survival. The impact of these efforts extended far beyond 1945. The institutional knowledge gained, metallurgical processes, precision manufacturing, testing protocols, formed the foundation for post-war aviation, jet propulsion, and the aerospace industry. What began as a response to a deficiency became a defining feature of American technological capacity. Radial engines were a lesson in resilience, the ability to transform scarcity, uncertainty, and industrial inexperience into a reliable, scalable solution. Above all, this story reminds us that the quiet work of engineers, machinists, and scientists can shape history as decisively as any battlefield maneuver. In the hum of a factory, the glow of a test cell, or the tight measurements of a crankshaft, the future of warfare and of industrial capability was being written. It is a testament to human ingenuity under pressure and to a nation's capacity to meet unprecedented challenges with discipline, creativity, and patience. The engines themselves became more than machines. They were symbols of a lesson that endures. That mastery of material, method, and process often determines the difference between preparedness and vulnerability, between opportunity seized and opportunity lost. In the skies of World War II, and in the decades that followed, that mastery would prove invaluable.